All right, good afternoon, everybody. We're going to begin the next session. So I'm David Edom, part of the NNSA Office of Advanced Simulation and Computing. I'm filling in for Cy Hammond as a moderator. He couldn't be here this afternoon. So we have three presenters to round us up here. So our first is Kaishu Mason from the University of Pennsylvania. His field is statistics, and his advisor is Dr. Nancy Zhang, and he did his practicum at Lawrence Berkeley National Laboratory.
Thank you for the introduction. So today I'm going to be talking about some work that I spent my last year of my PhD on, which was on a data subsampling method for making our methods for spatial transcriptomic data more scalable. So to start, I'm going to give you an example of what spatial transcriptomic data looks like and why it's important. So this example here is of a colorectal cancer patient from a technology known as Visium HD. This data contains about 500,000 cells, and each cell is classified into one of 15 cell types as colored on the left, and 5 niches or regions as colored on the right. And so the data that we work with here is going to be a matrix, where each unit of observation, or row, is going to be a cell. And for each cell, we get the spatial coordinates, both x and y, some high-dimensional response vectors such as gene expression, and then its cell type. And the reason why we really care about this spatial dimension is that a lot of the functions of our cells differ depending on their context. For example, regions of the brain or a diseased tissue versus a healthy tissue. So for example, with spatial data, we can ask a question of how's the role of a fibroblast change when it's near a tumor? So we start with our cancer data, and we can define regions. Here, let's just say the red region is tumor, and the blue is healthy. We can then isolate the fibroblast in this region. And if we look at the expression of a gene, let's say COL3A1, we see that the expression is increased in the tumor region. And so we can answer a question saying, well, we think that COL3A1 can be implicated in how a fibroblast responds to a tumor. And this question is really just part of a more broad set of questions known as differential testing. So with differential testing, we're really just asking how does some response Y change with the levels of some stimulus X. So for example, we start with our cells, and our X here is going to be region, so you can one-hot encode, I guess, the 5 regions that we have. Our Y is going to be gene expression, so we'll be doing this for each individual gene. And for each cell type, we can isolate which cell types are in our tissue. And so generally what we do is we fit a separate model for each specific cell type. So in this case, I'm going to fit something known as a generalized linear model, or GLM. And from there, you get a beta vector for this cell type. And we're going to do this for all cell types to get a matrix. And the two things to keep in mind are that we're going to be running this for all 20,000 genes, and we're also going to be running it for all 20 or so cell types. So we're running around 400,000 models for each data set. And one more thing is that we're not really getting observations on the units of cells, but rather something slightly different, which means the models that we use in practice are a little bit slower. And because of this, the size of our data set really matters. So between 2009 and 2024, we were sort of operating in a domain where the bottleneck of research was in generating high-quality data. And so our sample sizes were really on the order of between 5,000 and 20,000, which meant our models to fit them all would take around a couple minutes to a couple hours, which was no problem. However, now in 2024 and 2025, our data sets are really on the order of hundreds of thousands or millions. And now there's no problem in getting high quality data, but there's a problem in fitting our models efficiently. And so we really had to ask ourselves the question of why do we have large scale data in the first place? And to give an example, we're going to come back to our colorectal cancer data set. And on the full data set, we see that the vast majority of cells are going to be tumor cells. And furthermore, of the tumor cells, the vast majority lie in this purple region or this green region. And so we can see here that big data is really useful for identifying really small effects in very common cell types. And this is not really that important because usually the larger effects are what we care about. However, it is also important for identifying moderate effects in very rare cell types. For example, even though the cell type on the far right might be 1% of your sample, with 500,000 cells, you still have a sample size around 5,000, which is pretty adequate. And so what we want to do is we want to exploit the redundancy in our data by doing some subsampling prior to analysis. So for example, here, our subsample, maybe 30,000 cells, will be downsampling the tumor cells relative to the rest of the cell types. Furthermore, within the tumor cell types, we probably want to have more cells or more tumor cells that lie in these rare regions compared to the more common regions. And so what we want to keep in mind is that an ideal subsample should have comparable power to the full data set. And so now I'm going to talk about the state of the art and what people do for doing subsampling prior to analysis. The first one is known as rasterization. So in rasterization, we start with our tissue, and we segment the tissue into these S by S regions called squares. And S is going to be a hyperparameter you can tune. You'll then aggregate all the information of all cells that belong to your region, and from there, you essentially get a coarser data set, but at a much smaller sample size, so you can run your analysis faster. The second method is known as geometric sketching. So in geometric sketching, you first embed your cells into a lower dimensional subspace with something like PCA, and then you sample uniformly within this subspace, with the idea being that by doing so, you'll be oversampling these rare cell types. And while both of these methods are very useful, they have two major flaws. The first is that there's no real natural stopping criterion, so in neither of these methods can you know exactly when you want to stop. And the second is that they're feature set independent. So you'd imagine that if you really cared about, let's say, one specific feature in your data set, you'd want to oversample cells to have this feature. However, since these cells don't even look at your feature matrix X, you're going to get the same subsample no matter what your scientific question is. And so we've made a method Sparrow which aims to solve these problems. And before I talk about what Sparrow is, I'm going to show you the results on our colorectal cancer data set. So essentially, for all 20,000 genes, what we're going to do is test to see whether gene expression changes between regions for each cell type. We can do this for all gene cell type region combinations and get some list of significant effects. And then we also want to run this on our subsample data set. And when we do so, we have this recall plot here, where the y-axis shows the recall, and the x-axis shows the Q-value on the full data set. So the ones further on the left are more significant effects. Well, we see that our method Sparrow achieves almost a 90% recall, whereas the other methods achieve a recall that's worse than random selection. And so now I'm going to talk about what the Sparrow method is and what differentiates it from the other methods. But first, I need to go over some notation. We're going to let y and x be a data set where y is related to x through a generalized linear model. We're going to let S be a subset of the indices from 1 to n with size k. And we're going to let xs just be the subsampled feature matrix. And here, our goal is going to be to choose a subset of size k that maximizes your power with respect to testing whether each of your individual beta values are equal to 0. And our method Sparrow essentially boils down to approximating this power via minimizing the trace of x transpose wx inverse. The reason why this is the case is that for a generalized linear model, the standard error matrix has the form x transpose wx, which means that by minimizing this trace, you're sort of minimizing your standard errors, and since standard errors are inversely proportional to the power, you're sort of, in a sense, maximizing your power. And so generally, we still have the problem of having to choose this subset, and choosing a subset requires you to look over all n choose k combinations, which is basically impossible. However, we're going to leverage the fact that this inverse trace of x transpose wx inverse is a submodular function. A submodular function is one that exhibits marginal or diminishing returns. So imagine here that x and y are set functions, and x is a subset of y, and you want to add an element z. The marginal gain by adding an element z is going to be greater when you add it to x than when you add it to y. So that's the diminishing returns effect. And the idea here is that when you have a submodular function, greedy selection is able to get a powerful subset that gets like 0.6 of the optimal objective. And so really what we can do is we can just do a greedy algorithm where we start with an empty set S. And then from our feature matrix X, on each iteration, we just select the most informative data point, where informative just means we're minimizing this trace here. And so now we have a way of selecting our data in a fast method. However, we still have to determine when to stop. And so for here, we're gonna show that the power, you can get the power of your method when you're testing the wall test based on your standard error and the true value of beta. And it has this closed form. Now, because we don't know the true value of beta, we're gonna have to assume some sort of distribution. And the way we do that is by having these two parameters. One is gonna be delta min, which is the minimum effect size that we care to compute. So for example, if you're running a Poisson regression and you only care about log-fold changes greater than like 5%, then delta min is gonna be 0.05. The second is gonna be this delta J. And delta J is based on the power on your full data set. And it's gonna be the largest effect size that your full data set cannot affect with power, basically 1. And we're gonna assume that beta J is uniform on this interval, which allows us to calculate the expected value of its power. And so our stopping criterion is just gonna be when our subsample data set, XS, has power greater than C times the expected value of the power on the full data set. And this C is gonna be known as a power retention ratio. And so this is a user-specified hyperparameter which lets you determine how many points you want to select. So for example, if you set C equal to something like 0.4, then you don't need to select as many points as when you make C equal to something like 0.99. And so how this works in practice is we can select our points in sort of an online fashion. So here's a power curve based on our full data set. And the area under curve is going to be the expected value of the power. Here, let's say we select some points like 10,000 points, and we see that the area under this curve is much less than the area under the blue curve. So we say we need to continue on. And then on the green, we're still not there. And then finally, once we're at the red point, we say, okay, the area under the curve is more than C times the area under the first curve. And so then we stop our algorithm. And so our total algorithm, FARO, just stands for submodular power adaptive data reduction for representative downstream analysis. And really all we're doing is we're taking this greedy algorithm step and we're putting on a while loop. With the while loop being you stop when you retain at least C of the power for all parameters. And so finally, I just want to talk about some simulation results. So what I did was I'm going to simulate a data set called the full data set. And I'm going to let the number of data points in the full data set be between n equals 10,000 and 10 million. I'm then going to select a subsample of this data set with a power retention ratio of 0.99, and we're just going to look at some plots. So what we first notice is that the power here is basically the same on our subsample data set versus the full data set as expected. But we also see that the size of the Sparrow subsample actually decreases after a certain point. And the reason why is that you can really divide the algorithm into two distinct phases based on n. The first is going to be phase 1, where your full data set, there isn't enough data points to accurately detect effect size of size delta min with probability essentially 1. And so in this phase, adding more data is actually really important because it increases your power. And so we see here that the size of the Sparrow subsample increases linearly with the size of your full data set. In phase 2, which is in blue, your full data set, now you have enough data to accurately detect effect size of size delta min, which means that really adding more data, the only purpose that serves is to make your sampling more efficient. And so we see that the size of the Sparrow subsample actually decreases, and as expected, the runtime also decreases. And so what this means is as n gets larger and larger, once you're in phase 2, your runtime after subsampling Sparrow will actually plateau. And so it's not just scalable, it's ultra scalable. Yep, that's it. So just want to thank my advisor, Nancy, here at the front, and Alva here. She helped me a lot with this project, with a lot of the data analysis. And obviously the DOE as well. They really helped me not have to do TAing and doing my own research. So yeah, thank you.